Right, this little talk is on transfer functions, and within transfer functions we have two properties, things called poles and other things called zeros. They form the central plank of all analysis in flight control system design. And if we look at the learning objectives of this particular lecture, then the first thing is to become familiar with the idea of what a transfer function is. And be able to work out a transfer function from a differential equation. We then need to understand the concepts behind Laplace transforms and be able to take a transfer function and split it into partial fractions. Once we've split it into partial fractions, we can then use the Laplace transform method on the partial fractions to produce either impulse response, step responses, or ramp responses, and that's going to be the main set of objectives behind this lecture. Right, this little talk is on transfer functions, and within transfer functions we have two structures called poles and zeros. We'll explain what those are as well. The idea of transfer functions was originally developed by a French mathematician called Laplace, and he was an astronomist and a physicist, and he led some work in calculus, which then led to the concepts of Laplace transforms. And the idea behind the Laplace transform was that we could start off with some linear differential equation and convert this into something called a transfer function. And the transfer function facilitated different, more advanced types of analysis, particularly in the time domain and in the frequency domain. So the transfer function became an ideal vehicle for analyzing flight control systems. The transfer function itself was almost always called g of s. Any textbook, anyone doing flight control, will call the transfer function g of s, and it relates the output of a system to its input through an operation called a transfer function g of s. Now, one of the things about a transfer function is that it is a linear function and not a non-linear function. If we look at aircraft dynamics, then we split in general aircraft dynamics into two types: longitudinal and lateral dynamics. Longitudinal looking at forward velocity, changes in height and changes in the pitching motion, whereas the lateral dynamics look at side slip, rolling and yawing of the aircraft. And when we look at the dynamics, we notice that the dynamics are actually non-linear. So we have non-linear equations which describe aircraft dynamics at the start. You can tell they're non-linear because they've got things like square terms and sines and coses in. So these are non-linear terms. If you've got some linear terms like y equals mx plus c, that's like a linear equation, whereas y equals ax squared plus bx plus c would be a non-linear expression. So one of the things we need to do when we're doing transfer function work is to take some non-linear equations of motion and convert them into linear equations of motion. And we can do that through a process of linearization, and I'll cover that in the next lecture. But for the moment, we could convert our nonlinear equations into linear equations, and these have got now no squares or square root terms in, and all the sines and coses have gone. Notice there is one sine term here in this expression, but this is more related to the angle of attack of the aircraft, which tends to be fixed. And then we just look at small perturbations about that point. Similarly, for the lateral motion, we can also obtain sets of linear differential equations, and these two sets of equations will form a significant part of the flight dynamics course in the 3rd year, and if you did the MEng, in the 4th year. Now let's go to look at a transfer function itself, where it comes from. The underlying idea here is this one here, that if we've got some term dy by dt, we can represent this by s times y. So the d by dt term we can represent by s, and d2 by dt squared by s squared, d3 by dt cubed by s cubed. So if we've got some differential equation like this one, we could replace this term here by s squared and this one by s to give us a polynomial expression here, which we could then rearrange into this form here and then factorize into this form here. Now this function here then is called the transfer function, and it's come from the original differential equation, replacing differential terms. That's d by dy by s, d2 by dy s squared, d3 by dt s cubed, if it was a higher order, putting those back into the original differential equation, converting it from a differential equation into a polynomial in s, and then rearranging it into a output is something times the input, and that is called the transfer function. And we can also factorize this to give us a factorized transfer function. For general case of an nth order polynomial in terms of the output y, an mth order in terms of the input u, we could then replace dn by dt to the n by s to the n. We could replace this term by s to the n minus 1 and go all the way down here until we get to a0. We do the same here. This will become s to the m, which will become that one there, and then rearrange, and we could get a general transfer function of this form. So it's possible to take any general differential equation and convert it into a general transfer function. So that's a very useful trick, but it does rely on the fact that these equations here are linear. Now, within the transfer function itself, we can do an extra thing, which we can factorize the transfer function. So if we went back to here, if we were to factorize now this transfer function here, so one thing we could do is to take our transfer function and factorize it, and this gives us a new way of looking at a transfer function. In terms of the top line, it now factorizes into a series of factors, and the bottom line will factorize as well. Now in this particular case, we've considered them to be first order factors, but you could have second order factors as well. You can't have third order factors. And the top line now are called zeros. So these things on here at the top called zeros, and the things on the bottom are called poles. So if we have a quick look now at changing, say, a pole or a zero to see what effect that might have on the dynamical response of the system. So here's a little system here which has got 1 0 and 2 poles, and we can change now the zero in the system to look at what happens. If the zero is bigger than the biggest one of these two, then we're going to get some what's called overshoot in the system. If T1 is bigger than TD, we'll tend to get what looks like a non-overshooting or first order response. And if this coefficient TA is negative, we'll actually get the system going the wrong way at the start. So let's look at those in terms of what they might look like. So for certain parameters, we're going to get, this is called a step response here, so it's going from one value from 0 to 1, and in this first case we're getting a very big overshoot here, and in another case we're hardly getting less overshoot as we change the 0, and eventually we get a response that looks quite with non-overshoot. As the 0 gets further, it gets slower, it slows down, and eventually if you choose negative values for the 0, it'll go the wrong way first. Now it turns out that a lot of aircraft flight dynamics have this feature of going the wrong way first. In other words, negative values for the 0s. And this in general, for control purposes, is bad news because it makes the system more difficult to control. As an example of this, when an aircraft changes altitude and there's a movement in the elevator induces immediately extra change in elevator, induces extra drag on the aircraft. The extra drag forces the plane to slow down a bit, which then causes it to lose height. So you're actually trying to use your elevator to gain height, but initially what will happen is the aircraft will lose height. So it'll start to go down, but as the airflow develops, the lift on the wings kicks in and it starts to gain height. So initially the elevators introduce extra drag and it goes down, and as the elevators and the airflow kick in and you get the aerodynamic lift, it starts to lift and it changes height. And so in lots of flight control systems, we do in fact have 0s which are negative. Now let's look at effect of changing poles. So the poles are the thing on the bottom line of the transfer function, and if we look at two very simple systems, one is 1 over s plus 3 and one is 1 over s minus 3, and if we plot the poles in a real and imaginary axis, this is s plus 3 equals 0, so it's at minus 3, and it would sit down here, and the s plus 3 equals 0 equates to s equals plus 3, which is over here. Now interestingly enough, anything on this side of this is the imaginary axis down here, we define as being stable. Anything on this side we define as being unstable. The details of this we will look in further lectures, but just for the moment we could consider these two cases, and if we do some analysis on these, which we'll be looking at in a subsequent lecture, the time domain response of the plus 3 has an e to the minus 3t in it, whereas the minus 3 has a plus 3t in it. Now this is a decaying exponential, which is why we call it stable, and this is a growing exponential, which is why we call it unstable. So if we look at the time responses of these, we can see that e to the minus 3t is a decaying exponential, whereas e to the 3t just grows and grows and grows. This is like my debt, just grows and grows and grows. And this is what you really don't want. And that's arising because the pole is on the wrong side of the imaginary axis, and we call it unstable. So from this, we can see we can get effects of 0s on the system, which might be undesirable, effects of poles on the system, which might be undesirable. And all of these features are really coming from analysis of this thing called the transfer function. So the transfer function becomes the main vehicle for carrying out analysis in flight control systems. And as I say, it's obtained by converting linear differential equations into a transfer function, and then the top line can be factorized into 0s and the bottom line can be factorized into poles. We'll now look at a brief tutorial session where we'll go into this in a little bit more detail. Right, this little talk is to back up our work about transfer functions. And the thinking here is that we start off with some differential equations. We can convert those into a transfer function, GS, And this can be factorised into two polynomials. One is at the top line, we call it ZS, the zeros, on the bottom line PS, the poles. So differential equations, transfer functions, zeros and poles. And let's look at a little example of this. We could have, say, a simple one, let's say dy by dt equals, let's say, 4y plus 2u. Just going to swap my pen because it's working very well. And the main thinking in going from differential equations to transfer functions is that we have the following little tricks up our sleeve, that d by dt represents as s, d2 by dt squared is s squared, and say d3 by dt cubed is s cubed. We could go on in there indefinitely, but what we do is we're converting differential equations into polynomials through these transformations. And these transformations came from some chap called Laplace. My pens can work a bit better. So here we've got dy by dt. This is a d by dt term, which is, we could replace with an s. So you could rewrite this as sy is 4y plus 2u. And then we can collect all the y terms on one side. This is an s, not a 5. And so we'll get s minus 4 times y equals 2u. And then we can rewrite this then in the transfer function. We have an input here, u, and an output there, y typically. So we can rewrite this as y equals, so we can get that y equals 2 over s minus 4 times u. And then the 2 over s minus 4 is the transfer function. In this case it's got no zeros because there's no polynomial s, it's got no zeros. Has got a pole, one pole, s is plus 4. And the way we work out the pole is we take the polynomial there and equate it to 0. So we get the equation s minus 4 equals 0, or s equals plus 4. So look at some other examples. Here's another one. This time it's a d3y by dt cubed plus 5 d2y by dt squared plus 12 dy by dt plus 8y is given by du by dt plus 2u. So here you've got slightly more complicated to understand. This is a third order differential equation because it's got a 3 in there. And so we can replace d3 by dt cubed with s cubed. So you can write this as s cubed times y plus 5s squared times y plus 12s times y plus 8y. Du by dt will be su plus 2u. So now we've got s cubed, s squared, d by dt s, they remain the same, d by dt s. We can now take out u and y as common factor. So we get s cubed plus 5s squared plus 12s plus 8 times y equals s plus 2 times u. What we need for the transfer function is y equals, so we can get that y is given by s plus 2 divided by s cubed plus 5 s squared plus 12s plus 8 multiplied by u. And then, so here's our differential equation, and now here is our transfer function. Now one of the things we might want to do is to factorise the transfer function. In this form it's interesting, but it's better if we got it in poles and zeros. So you could rewrite this now as s plus 2 divided by, now we've got to factorise this. So this one comes out now as s plus 1 into s squared plus 4s plus 8. If we just check that, it's going to give us s cubed, 4 and 1 is 5s squared, 4 and 8 is 12, and 1 times 8 is 8. So in this particular case now, we have our differential equation. We've got 1, 0 at s is minus 2. And then for the poles, we've got a pole at minus 1. And then we've got the s squared plus 4s plus 8, which we could factorise. So we can do that using the minus b plus or minus the square root of b squared minus 4c over 2a. And in this particular case, it comes out as minus 2 plus or minus 2j. So in this case, we've got a real 0, a real pole, and a complex pole as well. And then this then would be the transfer function representing the system. We can only get two types of pole, a first order pole or a second order pole, and so we'll be looking at first order poles and second order poles in separate lectures. The other thing that could occur is if we got a negative sign here, that can influence the transfer function, and if we've got a negative sign, say there, that could also change the response of the system in terms of its dynamic behaviour. So positive and negative signs can have an impact on the performance as well, and we'll need to investigate that through our work using Laplace transforms. For the moment, they are positive. So there's some examples now of going from differential equations to transfer functions. So you can have a little go now at going from differential equations to transfer functions. See if you can do these. Quick little test for you. Say we've got a differential equation d2y by dt squared plus 6 dy by dt plus 4y equals 2 du by dt plus 6u. So have a little go now at converting that into a transfer function between y and u. So I'm just going to do this one for you. So the first thing is, so d2 here, so d2 is s squared, so it's going to be s squared y, plus 6 dy by dt is going to be sy plus 4y is 2 du by dt will be su plus 6u. We're going to take y out as a common factor, so we get s squared 6s plus 4 times y equals 2s plus 6 times u. And then we can move this one underneath there to get the y equals 2s plus 6 over s squared plus 6s plus 4. And that's all multiplied by u. And so here's our differential equation, and here is our little transfer function. And in this particular case,
probably this has got two real roots. I can't think of what they are, but you could factorise those. And this has got a real 0. So that's how we go from differential equations to transfer functions to then zeros and poles.
Right, this talk is on Laplace transforms. Laplace transforms is a technique, mathematical technique for solving differential equations to obtain solutions in the time domain. And this technique involves converting the original differential equations, transforming them into some Laplace equations, solving them in the Laplace domain, and then taking the inverse Laplace transform to get back to our original time domain solution. So thinking is problem in the time domain, convert it to the Laplace domain, obtain the solution in the S domain, the Laplace S domain, take the inverse Laplace, and we get our time domain solution. So if we do have linear differential equations, we could go straight to the time domain if we were very clever, but we're not that clever, so we need to do Laplace transform, do some algebra, get the Laplace solution, and go back to the time domain. There's another technique for going from here to here called simulation, which uses numerical integration to do it, and that has been embodied into a package called Simulink, and we will be looking at an alternative way to get around this way, an alternative way using Simulink. And probably because a computer's been popular today, the Simulink domain technique is now surpassing the Laplace technique. But it's a very useful one to know, the Laplace. And this is the Laplace's equation. On face value, it looks quite a complicated expression, and one might think that carrying out this type of analysis is quite tricky. But fortunately, in practice, it turns out to be a lot easier. And one of the main things that we need to know is, as well as Laplace transforms for the system itself, which we now know is in the form of transfer functions, we'll also need to have a Laplace transform for the type of response we want from the system. Now, there are a number of responses we can have: impulse responses, step responses, ramp responses, exponential responses, or sine wave responses. So an impulse response goes up and then comes rapidly down, so just as an impulse of 1 unit. Step starts at one value, steps up to another. A ramp continuously increases. An exponential function increases exponentially, a bit like COVID-19. And a sine wave keeps on going up and down like this. So if it's COVID-19, it would come back as a second wave here. And the functions here are: impulse is s, is 1, step is 1 over s, ramp is 1 over s squared, exponential 1 over s minus a, and sinusoid 1 over omega squared plus s squared, where omega is the frequency. And we have to remember these when we're doing our Laplace analysis. So here are some of those. Step, Laplace transform of a step. There's 6 of these that we need to know to do the analysis. Step response is 1 over s. A ramp is 1 over s squared. This is a time domain. This is Laplace transform. Next one is an exponential, and e to the minus at is 1 over s plus a. And a t e to the minus at is with time in it as well, is given by 1 over s plus a squared. E to the minus at cos bt, this could give you a oscillatory type response, is given by s plus a over s plus a squared plus b squared. This process down here is called completing the square. So we have to have this as s plus something squared and a separate number in there. And you see the same term here in here to represent this particular term. So This one's more complicated, but we will use it later on. Sinusoidal term of the similar type doesn't have the s plus a here, it just has the b. So it's b over s plus a squared plus b squared. So we'll have to remember those 6 terms. So, and then we have inverse Laplace transforms, which are just basically the inverse of what we just seen. So inverse Laplace of 1 over s is 1. Inverse Laplace of 1 over s plus a is e to the minus at. Inverse Laplace of b over s plus a squared plus b squared is e to the at sine bt. And inverse Laplace of s plus a over s plus a squared plus b squared is e to the at cos bt. So these are the 4 main useful inverse Laplace transforms that we have to remember to do the analysis. And so this is how we could do it. First of all, we choose the type of response we want. So it could be, say, 1 over s. We get our transfer function gs, and then we multiply this by this to get an overall function. Then we take that overall function and we split it into partial fractions, and then we take the inverse time domain solutions, inverse Laplace transforms, and we'll get the time domain solution. So in principle, it's a little bit long-winded, but it does work nicely. Just to remind ourselves about transfer functions, so if we got a function like this, we could replace d2 by dt squared by s squared, d by dt is s, and we could go from this to a transfer function. So, and then just remember our types of input as well. So we've got the impulse, step, ramp, exponential, sine. The one is tends to be used most of the time is the step, which is 1 over s. This is used 90% of the time, the step response. So let's take a simple example. Here we have 2 over s plus 4 as our transfer function. The type of step response we want is a step. So because it's a step, it's going to be 1 over s. So we then multiply this by this to get this term here. And then split this into partial fractions. I'll do some partial fractions for you, just remind you how to do them in the tutorial. And then having got from here to partial fractions, we then use the inverse Laplace transforms of each of these to get the time domain. So the 0.5 gives us the 0.5. 1 over s is just 1. So that gives us 0.5. 0.5 gives us the 0.5. And 1 over s plus 4 is e to the minus 4t. So this gives an expression now for the step response of this system as 0.5 minus 0.5 e to the minus 4t. What we've done is taken the original transfer function, multiplied it by the type of response you want, which is the step, to get this, split into partial fractions, then taken the inverse Laplace transforms to get the time domain. And this is essentially how you can go from a differential equation plus a type of response to a time domain solution using Laplace transforms. Here's another example. This time we've got 2 over s plus 2, s plus 4. Again, step response, so we multiply this by this to give us the overall function here. Then we take this function, split it into partial fractions, gives us 3 terms this time. The 0.25 is a 0.25, the 1 over s is a step, so that's 1, minus 0.25, minus 0.5, sorry. Then 1 over s plus 2 is e to the minus 2t, 0.25, 0.25, 1 over s plus 4, e to the minus 4t. So then we have an expression then for the step response to the system, and we could put different values of t in there, where t would be time, plot the graph out, and we would get the step response. In the case of a second order system where it can't be factorized, it can get a little bit more complicated. So let's have a look at that one next. So let's say we got s plus 1 over s squared plus 4s plus 5. We're looking at the step response, so it's going to be 1 over s. So we could take this function out, split it into partial fractions. We could use like different techniques for getting the coefficients. One is to like compare coefficients of different orders, like coefficients of s squared, coefficients of s to the 0, and then compare both sides. We'll look at those techniques in detail in my little revision lecture. But let's assume we've gone from here now. Here's our partial fractions down here. Now, because it's a second order system, this one now has to have these type of responses in. which means we have to take this function here and split it into two parts. So this function has to be split into two parts, one to represent the sine, one to represent the cos. So we complete the square, so it's s plus 2 squared plus 1 on the bottom of each. That's converting this into this. But now we need an s, because we've got an s plus 2 here, we need an s plus 2 there as well, and a number in there. So we know we have to find that number and that number then by solving this equation. So again, I'll show you to do that. But in this particular case, it comes out as 0.2 and 0.6. And then when we take the inverse Laplace transforms, we've got the a alpha, which is this part here now, so it's going to be 0.2 over s, so it's going to be 0.2. And this part here minus 0.2, and this is e to the minus 2t cos t. So it's that number there goes in there, and that number there goes in there. And this is a sine term, so it's 0.6 e to the minus 2t sine t. So this is a slightly more complicated expression now, because for a second order system, we get a sort of a response that oscillates, and in oscillating, it has to be represented by a cos term and a sine term. Here's just a little bit more detail on that last bit of analysis, but we'll go over this in the tutorial which follows immediately after this.
Right, this little talk is on recap of Laplace transforms, and there's a number of things we need to know when we're doing Laplace transforms, but overall it's quite a complicated analysis, but it's actually quite simple to do. And the idea is we've got some linear differential equations which we want to have a look at the time domain solution for. So time domain is usually a graph of output against time, and we call this the transient response. So we might be interested in having some certain type of input going into our system and knowing what the output looks like. And in Laplace transforms, the main three inputs that we can apply are an impulse, and the Laplace transform that is 1, a step, which is 1 over s, and this is the one we use 95% of the time, and a ramp, 1 over s squared. So we have different types of input, and we can then obtain the different types of input transient responses. Bit of a spider there. Now, the other thing we'll need to know is, when we've done our analysis, we'll need to know a little handful of inverse Laplace transforms, and the inverse Laplace transform of 1 over s is 1, the inverse Laplace transform of 1 over s plus a is e to the minus at, and then we have a couple of second order terms here which have got sines and coses as well. So this is b over s plus a squared plus b squared, which is e to the at sine bt, and s plus a over s plus a squared plus b squared is e to the minus at cos bt. So these are 4 things, inverse Laplace transforms, we need to use, and these are the 3 main inputs. And then we can, with that bit of background, we can do some problems. So say we've got a differential equation, which is, let's say, dy by dt is minus 4y plus 2u. And what we wanted to do now was to obtain the step response for this differential equation. So face value, this looks quite hard. But if we deploy now our Laplace transform technique, it becomes quite easy. So the first main trick with Laplace transforms is to recognise that d by dt is represented by the Laplace variable s. So we can replace dy by dt by sy equals minus 4y plus 2u, and then we can collect up the y terms. So you get s plus 4 times y equals 2u, or the y is 2 over s plus 4 times u. So what we've essentially done now is we've got ourselves a little transfer function here. Now we've got the transfer function, we can then decide on what type of input we want to get the different types of response, and we're going to go for the step response. So we now multiply this step response by the transfer function. split into partial fractions, and then take the inverse Laplace transform, and we'll get our time domain solution. So let's have a go at that. I just need a bit of space now to do this in. So we've gone from our linear differential equation to a transfer function, which is 2 over s plus 4. So let's just rub this out. It's not rubbing out so well, this. This is a bit of a problem. Got a new pen and it's a bit more nasty to rub out. Anyway, here we go. So, we've got 2 over s plus 4 is our transfer function. And we've got a step, which is 1 over s. So we'll multiply that by s, it's going to be s like that. So, next stage now is to split this off now into partial fractions. We can write this as a over s plus b over s plus 4. And now, the only tricky part now is working out a and b. So, to get a, we can use the cover-up rule to do this. So to apply the cover-up rule, we cover up, say we're working out the a, so we cover up the s here, and if we solved the equation s equals 0, we get the solution s is 0. So if I cover this up and put s as 0 in here, I'll get 2 over 4 plus a 0, so that gives me a half. So a is 0.5. To get b, b is associated with s plus 4. If I solve this, s plus 4 equals 0, I get s is minus 4. So what I do now is I cover up the s plus 4 here and put s as minus 4 in there. So it's 2 over minus 4. So b is minus 0.5. 2 over 4 with a minus in is minus 0.5. So I've now got my solution to my things. It's going to be 0.5 over s minus 0.5 over s plus 4. Then, having got to this stage, I now look for my inverse Laplace transforms. So I've got a 1 over s term is 1, so that's a 1 over s term there, but it's multiplied by 0.5. So I get y of t now, the time domain response. This equation now is this output graph here, y of t against time, and it's given by 1 over s is just 1, and 0.5 times 1 is 0.5. So it's going to be 0.5 minus, I've got a 0.5 here, and a 1 over s plus 4 is e to the minus 4t. And this now is the equation that describes the time domain behaviour of the system for different values of t. So you can now put different values of t in there, plot the graph, and we get a time domain solution. And in this particular case, it would probably look something like this. Like that. And if we make t very large here, e to the minus 4t would disappear, so it's going to go to 0.5. So that value there will be 0.50. So this is y of t against t, and it will come up to about a half, or come up to exactly a half. So this is an example now of where we could have gone from a differential equation to a time domain response using Laplace transforms. Right, so just going to look at another example now of going from a differential equation to a time domain solution using Laplace transforms. So we have a differential equation, let's say d2y by dt squared plus 3 dy by dt plus 2y equals, let's say, 4u. So these are what looks like a second order differential equation now, and we're going to try and get the time domain solution to this. So the first thing we need to do is write another term here. is to convert this now into a transfer function, then choose the type of input, multiply the input by the transfer function, take the inverse Laplace transforms, and get our time domain solution. So let's have a look at doing this. So d2y by dt squared will be replaced by s squared, so get s squared y plus 3sy plus 2y equals 4u. So we convert a differential equation into a polynomial. We can then take the y out as a common factor. So it's s squared plus 3s plus 2 times y equals 4u. Unfortunately now, this one factorizes into s plus 1, s plus 2. So we can now finally get our transfer function, which is that y equals 4u over s plus 1, s plus 2. Having got to our transfer function now, we can choose the type of response we want here. So we're going to go for a step response again. And we're going to multiply the step response by the Laplace transform, split into partial fractions, take the inverse Laplace transforms, and get the time domain solution. So again, I'll have to have a bit of space here, using a slightly different pen this time, so it's easier to rub out. So we've got 4 over s plus 1, s plus 2, that's our transfer function. And we're multiplying it now by a step response, which is 1 over s. So we get a little s in there. And this now we can represent as a over s plus b over s plus 1 plus c over s plus 2. And our trick now is to work out ABC using partial fractions. So, first one is s is 0, s is minus 1, s is minus 2 if you solve those equations. So to get the a, we cover up this one and we put s as 0. So 4 over 2 is 2. So a comes out as 2. That's handy. Next one is this one. So this is equivalent to putting s equals 0. This is s is minus 1. This is s is minus 2. Into this function, covering up the appropriate one. We're using this cover up rule. To get the b, we cover up the s plus 1, so cover that one up, and now put s as minus 1 in here. So I get 4 over minus 1, then minus 1 and 2 is 1, so that comes out as minus 4. So that's quite nice. It's going to be minus 4. Then, to get the c, we do the same thing. We need this term here, this one, so c is the plus 2, so cover this one up, and now put s as minus 2. So get 4 minus 2 and 1 is minus 1. So minus times minus is a plus, so it comes out as, in this particular case, 2 plus 2. So we've now got the partial fraction coefficients, and what we have to do next is to take the inverse Laplace transforms. So the first one is 2 over s. So we can get that expression now, y of t, and so we're going to get a 2, and then 1 over s is just 1, so that's 2 times 1 is 1, minus 4, then a 1 over s plus 1 will be the same as e to the minus t. And then we've got a plus 2, and this time it's plus 2 here, so it's going to be e to the minus 2t. And then this then is the equation for the step response. As we put different values of t in here, we can plot a graph, and again we get a little graph which would look at something like this, and this would be a graph of T against T. This value along here, call this the steady state value, and you can get this by putting T large into here. So that disappears, so that's going to be 2, isn't it? So this distance here will be 2 units. The exact shape we'd have to get by putting different values of T in, putting some points on, and then joining the points out to get the graph. So that's another example now of going from a differential equation to a time domain solution, and those have just used these first 2. Now the next one's a bit more complicated. We're going to use these 2 as well. So this one's a bit more, but you can see it's more complicated, but it's not that very complicated. Right, so now we've got another example we're going to do. This is again a differential equation here, and we're going to try and get the time domain to a step response to the system, and this time we're going to try and deploy these 2 down here, which have got the sines and coses in. So this one's going to be a little bit more advanced than the previous one, but the first thing we do is convert this now into a transfer function, multiply the transfer function by the 1 over s, then convert it into partial fractions, and take the inverse Laplace transforms, and we get our time domain solution. So let's have a go at this. So d2y by dt squared will be s squared, so we get s squared times y plus 4sy plus 5y is su plus u. So we can then take out the y's and the u's, so we get s squared plus 4s plus 5 times y equals s plus 1 times u. Then take this term, so my pen's not working very well here. Take this term underneath here, so we get that y equals s plus 1 over s squared plus 4s plus 5 times u. And so now we have our transfer function for the system from our differential equation, and now we're going to multiply the transfer function by the step and then split it into partial fractions. So let's have a go at doing that. So we're going to have s plus 1 over s squared plus 4s plus 5 multiplied by the s, which is the step response. I'm just going to move this slightly. So you can have s plus 1 over s squared plus 4s plus 5. We just need a bit more space. We rewrite this now as a over s plus bs plus c over s squared plus 4s plus 5. So this time it's a little bit more complicated partial fraction, and the cover-up rule now doesn't work quite as well. So what we're going to do is we're going to multiply both sides by this term here on top. So if we multiply that on top, the first term will disappear, and we get s plus 1. If we multiply this by this, the s will cancel, so we get a into s squared plus 4s plus 5. And then if we multiply this by this, we'll get bs plus c multiplied by, this will cancel with this, and we're left with the s. That's just multiplying everything through all this equation by this term here. Now we can do is we can do a compare coefficients to work out a, b and c. So let's have a look at this now. Which one should we go for first? Should we go for coefficients of, let's say, the term with no, so we've got 1 on this side, so it's coefficients of s to the 0, so we've got a 1 on this side, and on this side we've got 5a, and we've got no coefficients to s. So we can get that a now is 1 over 5, so a is 0.2. So that's our first one done, a is 0.2. To the next one, we'll do the coefficient of s to the 1. So s to the 1 on this side, it's a 1 in there, so that's going to be 1. And s to the 1 this time will be 4a, and this time we'll have c. So now I've got the equation of 4a plus 1 plus c is equal to 1, but we know now that a is 0.2, so this is 0.8. So if 1 plus 0.8 adds up to 1, then c must also be 0.2. That's quite good. The last one now is to get the b. So to get the b, we need the coefficient of s squared. So on this side, there's no s squareds, and we've got an a here plus ab. So we now know that a plus b is 0, but we know now that a is 0.2, and therefore b must be minus 0.2. It's going to be minus 0.2 there. So we've now got our transfer function split now into the partial fraction form here. So we can get away with this. Now this one's a bit more tricky, so we're looking now at this now, at our table here, to see how we're going to fit it. So we can see that the first term goes with this one, so that's quite nice. But now we've got a more complicated term here, and this one now doesn't seem to fit in with either of these, because this one doesn't factorise very easily. So we're going to try one of these now. So we need to write now s squared plus 4s plus 5 as s plus a squared plus b squared, as s plus a squared plus b squared. Work out what a and b are. So we can see from this now that if we make a as 2, then this is going to give us an s squared plus 4s plus 4. So this gives us s squared plus 4s plus 4, and therefore b squared must be 1 if b squared is 1. Right, so here we go now. So we've got our partial fraction form of this, and next thing we need to do is to convert this into a form of s plus a squared plus b, and we can do that by noticing if we put an s plus 2 in here, then we get s squared, 2 2's of 4, and another 2 2's of 4, 4 on that side, 5 on this side. That's got to be a 1. So we can rewrite now this term here as minus 0.2s plus 0.2 over s plus 2 squared plus 1. Now the problem we've got now is this term here now doesn't fit into either of these two formats here, so we'll have to slightly adjust it now to have this now will have to be equal to a combination of these two terms. So to do that, notice that we've got an s plus 2 here, and we have an s plus 2 in there as well. So if we start off with this term here, this could be split now into alpha into s plus 2 over s plus 2 squared plus 1, and then we have a beta over s plus 2 squared plus 1 as well. This term here would be that term, and this term here would be this term. And what we're going to do now is work out the alphas and betas. So if we multiply, this has got to equal to this. So if we multiply everything by this term, we can delete those. And so we can now see that alpha, so then we get essentially this equation, this part here, we've got alpha into s plus 2 plus beta equal to 0.2s plus 0.2. So looking at this now, the different coefficients, obviously alpha has got to be minus 0.2, that's going to be minus 0.2, and this is minus 0.2 and minus 2.2s, and this has got to be 0.2 at the end. Then beta, so this is going to be minus 0.4 plus beta is 0.2. So the only way we can achieve that is with beta as 0.6. So with beta as 0.6. Then we've got to include so that's this term here, is this one, which are these two. So if we include now the 0.2 over s, then we get our final Laplace transform formula. And then what we can do now is convert now this one back now into the time domain. So 0.2 of s, so we now get an expression for y of t equal to 0.2, because 1 over s is just 1. And I've got minus 0.2, that's this 0.2 here. Now I've got s plus 2 over s plus 2 squared plus 1, so that's one of these. That's going to be e. The a is 2 and the b is 1, so it's e to the minus 2t cos t. That's going to be e to minus 2t cos of t plus 0.6. I've got 0.6 in here. And this one now is one of these. So this is going to be an e to the minus 2t sine t. And this gives us our final expression now for the time domain response of the system. This y of t is 0.2 minus 0.2 e to the minus 2t cos t plus 0.6 e to the minus 2t sine t. And because we've got the presence of sine and cos terms, we're likely to get like an oscillatory response here. And so we could put different values of t into this, get some values of yt, get some points on here, like this, join them up, and we'd get the transient response. So there's another example now, slightly more complicated, of using these two terms in a differential equation to obtain a time domain response which has got some oscillatory behaviour with cos and sine terms in.
Okay, just before we finish off, here's another few little examples. This will include some conceptual stuff as well as how to solve the problem using MATLAB and or Simulink. And if you want to cross-refer to these, remember there's the extra lecture on transfer functions in MATLAB to look at as well. But let's have a look at this transfer function here. We've got 2s plus 1 over s squared plus 3s plus 2, and we could put that into MATLAB through the following little bit of code. Say num equals 2, 1, that's the 2, 1. Den equals 1, 3, 2, that's 1, 3, 2. And we use the command tf to get the thing as a transfer function called sys1. This might be handy for the next stage. Now, if we have some transfer function form here and we want to look at say the step input, then we multiply the two together to get us this function here, and then we split this into partial fractions, and then we have to work out the partial fraction coefficients, take the inverse Laplace transforms, and we get our solution. So when we split this up, it gives 0.5 over s minus 1.5 over s plus 2 plus 1 over s plus 2 s plus 1. So the 0.5 over s becomes just Laplace inverse transform is 0.5. This one is minus 1.5 e to the minus 2t, and this is plus 1 e to the minus t. So that then gives us an equation for the step response of this system here. So that's what we've been looking at in the lecture. Now, few little tricks. If we entered in n and d and the transfer function, there's a little command called residue which actually works out the partial fraction numbers for you. This is a very handy command. So you then, so for that should be a little n and a little d. Word or PowerPoint sometimes changes the case of a letter. So you've got, just watch that when you're messing about with it. Sometimes it puts a capital in there sometimes as well. But now this will be correct now. So if you run this code, it'll then give you an R, a P and a K. So K has to come out as an empty set for you to know it's done it correctly. And then these then are the poles. So we've got these are the numbers, sorry, these are not poles, these are the partial fraction top lines. So we've got a minus 1.5, which is that minus 1.5, the 1, which is the 1, and the 0.5. And then these ones here tells you which it goes with. So the minus 2 goes with the first one, so that's the s plus 2. So that chat sign changes to go in there. Then the minus 1 is the second one, which is the 1, which goes in there. And then the naught is like this one, s plus naught on the bottom line here. And so you can go this simple command, you can compute these and then get your partial fractions without having to think too much, just type in a few numbers. So that's a little trick up your sleeve. Now, so if we got this equation now, there's 4 ways we can solve this. First of all, we could just get our calculator out, put different values of t in here, get y of t, and then we could plot points, join them up, then we get this graph here. This is a little bit of MATLAB code now, which does the same thing. It sets up an array from 0 to 6 seconds, step length of 0.1. Here's the equation. Now, if you pass an array to this equation, it'll give you an array back, because MATLAB's quite clever like that. And then the plot command will plot one against the other. So there's how you could do the same thing now, rather than doing it by hand using your calculator. This is a little bit of MATLAB code that would do it for you. Alternatively, you could just enter in the transfer function and use the step command. And then the step command on this would give you the same graph. So all these methods will give you the same output. Final technique would be you could set this thing up as a Simulink simulation, put a step in and get a response scope here. And then that would give you the same thing. So if you've got some problem, like say this one, and you want to get the solution to this, then bear in mind you've got 4 different solution paths. You can explicitly work it out. You can explicitly work it out and get MATLAB to compute it. You can use a toolbox command step to get the step response, or you can simulate it in Simulink. So you've got a variety of methods of doing the same thing, and it's a good idea to try all 4 to get the same answers, because then you really know what you're doing. So if we have a learning objectives review, the idea behind this lecture was to become familiar with the ideas of transfer functions, be able to go from a differential equation to a transfer function, understand the concepts of Laplace transforms, then be able to apply partial fractions to the transfer function. So you can do that either by hand or you can do it using MATLAB. And then once you've got the transfer functions split into their partial fraction form, you can then use the transfer functions in that form to get either impulse response, step responses, or ramp responses. But in principle, we tend to go for step responses, and you can do that for using 4 different methods, and you can then see which ones you like best. So here's a little problem. 5s plus 1 over s squared plus 5s plus 6. Here's the step response here. It's quite a bumpy system, a bit like an Alton Towers ride. But you can have a go now, have a go at taking the 4 different methods that we've got. These 4 methods, have a go at these 4 methods and see if you can solve this problem using the 4 different methods. And here's a second problem, a little bit more complicated. Have a go, and there's the step response there. So see if you can solve this one using the 4 different methods. So that'll give you some confidence then that if you've got any transfer function, you can get the step response, and you know a variety of ways of doing it. That's going to give you a lot of extra confidence in tackling any problem you might meet in this area. So final thing is a bit of retrospective reflection. So you have 4 different methods now to solve the same problem. Manual calculations, manual using Laplace transforms, MATLAB solutions to the calculations, control system toolbox solution, and Simulink solution. So just think now what the advantages and disadvantages of the 4 approaches might be. And that might help you in deciding on when you're working in industry, if you've got to do this problem, how are you going to go about solving it. If I was doing it, I would choose two methods and then I'd make sure that both methods gave the same answer. This is one of the things you can do in feedback control. You can get the answers from a variety of approaches. If you take one path and you get one answer, to choose a different path, get the same answer, then the chances are that you've done it right. Because to take two separate paths and come up with exactly the same answer can only really happen if it's correct. So that's a useful tip there for checking your solutions. Always do it two ways. Here you've got four ways. You could just choose two, and that will give you a good idea what's going on.